Hello, everyone. I hope you are all having a great morning, afternoon, evening, wherever you are joining us from. And I hope you guys are really excited today for the second workshop for the Explore Expander Bootcamp, hosted by Polyhedra and Encode Club. Today we have a really exciting workshop by Dimitri from the Ethereum Foundation. So I will be inviting him up on stage so we can get straight into it because I know that's what you guys are here for today. So he is just getting ready to come up on stage and we can start the workshop. Yes, all very exciting. Hello, it's great to see you guys interacting in the chat. Hi, Dimitri.
Hello. Hi, Adriana. Nice to see you.
Nice to see you too. Whenever you're ready to share your screen and present, the stage is all yours. There we go.
Okay, great. Yes, hello everyone. Excited to be here, and thanks Adriana, Gente, and others for inviting me. I'm really excited to talk about our recent post-quantum aggregatable signature construction. Okay, fantastic. So yeah, well, again, I see there is a small chat down there, and I see there is a separate thing with questions. Okay, if I understand correctly, if you have a questions, please ask in the special folder, and I'll try to answer them. Some of them maybe during the call, or during the presentation, some of them later on. Okay, so let me start. So this is a joint work with my colleagues Justin Drake and Benedict Wagner, and also Mike Kudinov from Technical University of Eindhoven, who put a lot of contribution into this work. So we have started working on it several months ago with announcement by Justin on the Beam chain and the requirement of post-quantum cryptography to be deployed on it from the very start. You may know that recent years have called for kind of quantum improvements, and having spoken to many experts in the field, it's quite likely that we shall see a working quantum computer in the next decade, which can break a lot of current deployed cryptography at Ethereum. And because of that, it's desirable to come up early on with a solution that would resist such a powerful computer. And hopefully, over the course of time, we'll be able to improve it significantly so that actually the cost of switching from quantum to post-quantum is not that big. Okay, so let me proceed. So first, I'll explain briefly why we need aggregatable signatures. And the first slide, well, I actually forgot to insert the figure here, but you may all know how Ethereum works, that basically blocks are produced one after another, and they get signed by validators, and we expect quite a number of validators to be there. So the total number of them is close to 1 million, but every block is signed by a smaller number of validators, actually by about 32,000. And signatures are aggregated, of course, because each individual signature, if we put it on chain, it would be too expensive. And after all, we don't need that every signature is present there. We only need to establish the fact that a certain validator has signed. And for this, it's sufficient to have some sort of a proof that a signature is produced by a certain validator. And this proof is given to us by the notion of aggregated signature, whatever it is, even in the quantum setting or post-quantum set. Okay, so how it works right now. So right now, the signatures that we're using are so-called BLS signatures. That is a very secure signature scheme, dating, it's already like 20 years old, and it's based on elliptic curve cryptography. And the very nice feature of BLS signature is that its aggregation is very simple. So basically, we compute a linear combination of signatures, and this process is quite cheap. So actually, it can be done in kind of milliseconds on a normal machine if we spoke even about thousands of signatures. And basically, if someone wants to verify such an aggregated signature, the only thing we need to know is the so-called an aggregated public key. And if we have like a full list of validators, so if you see it on the picture, we expect about 32. So right now it's 32,000 validators sign in each slot, and the slot is right now 12 seconds. We want it to be smaller though. So right now these validators, they are organized in some kind of hierarchy. That's because if we had a single entry that would aggregate everything, that the bandwidth required to take all signatures is still significant, and we want it to be kind of lower. So right now they are organized in so-called committees or subcommittees of size 500, and 500 signatures, it's quite a small amount, so it's kind of several dozens of kilobytes. And how it happens, so yeah, for every subcommittee there are designated 16 aggregators for redundancy, and so all validators from subcommittee, they know the aggregators, they send signatures to all of them or to some of them, and aggregators also, we expect that some of them may be censoring, some of them not, but overall they produce an aggregated signature. And well, block proposers can sub-select some of those. They typically select the most the aggregated signatures that have the most validators inside. So basically, for every subcommittee, a signature with the most number of signed validator is selected. So after all, there are about 1,000 of aggregated signatures. Well, less if we don't include all the aggregators there. Well, in the future, what we think will happen is that thanks to the called orbit construction, we'll have the set of validators a little bit smaller, maybe 8, 16K validators per slot. And well, this will be a rotating set, and the principle of rotation depends on the actual stake of each validator. But overall, the principle should be the same. So we have like several thousands of validators, and we want their signatures to be aggregated. So well, here you see we don't employ any zero-knowledge machinery to verify, to aggregate signatures and to check the aggregated signatures, because BLS signatures have so nice internal structure that the aggregations is so simple and algebraic. Whereas for post-quantum signatures, the situation is a little different, and we may need a special mechanism to aggregate the signatures. Okay, so we quickly switch to the problem. Okay, let me try to see if there is a question there. Yeah, are the signatures of these subsets ordered by some algorithm? Yeah, well, I have to admit, I don't exactly remember how this is organized. So I know that there are some selection of these aggregated signatures by the principle of bigger bit mask, but I don't remember the details. It's deeper into the current kind of book of Ethereum consensus. So I would advise to ask there. Do people in the Ethereum Foundation see Orbit as the way to implement single slot finality? Yeah, it is one of the ideas, but I think it's kind of an important one, and it's likely to be implemented. There are some developments in this side. I don't follow all the developments there. It's better to ask people from the consensus team who are more into it. So for us, it's not really important how this is organized. It's just important to see the number of validators and to know that the setup is rotating. So as long as the validators are out there, we kind of design a protocol to sign and to aggregate the signatures. How exactly the set of validators is prepared is not important for this construction. So let's proceed then. Okay. Yeah. So the thing with current solution is that not only BLS signatures are quantum vulnerable, but also a lot of SNARK constructions that we may think to aggregate the signatures, as long as they are elliptic curve based, they fail because, well, everything elliptic curve based fails more or less. So we have to switch to SNARKs that are post-quantum, and there are not that many of them actually. So if we go into what we expect from a beam chain, then basically the picture that I have shown you becomes a little simpler, because we expect that aggregations will be done not into this well, little simpler. We expect that each aggregator should be able to accept all signatures, all signatures from the current set of validators. So as we see here, so by this yellow, each yellow circle denotes an aggregator, and yeah, again for redundancy, we expect several of them, but they all should obtain individual post-quantum signatures, and each aggregator then employs a post-quantum SNARK to create an aggregated signature. Well, ideally, so we shall look into the performance and kind of and into bandwidth. So ideally, there should be no second layer of aggregation. So ideally, all 8 or 16K validators should send their signatures to aggregator, and only one aggregation step happens. So ideally, there should be no aggregation of aggregations. We shall see. So it's very kind of performance dependent. So of course, if we have like a SNARK, a post-quantum SNARK, every post-quantum SNARK is able to prove about itself. So it will be possible technically to create a SNARK of aggregations if we want to compress it further, and if we see that it's not possible to kind of wrap them all up in a single step. But it's not desirable because it will increase the total latency, and we would like to decrease it. We would like to kind of decrease the number of hops here in the protocol. So each aggregator produce a post-quantum SNARK to aggregate signatures, and this post-quantum SNARK is put into, shall we put into a block. So basically, and post-quantum SNARK is the thing that is currently explored in this bootcamp. So as GKR protocol, as long as it uses post-quantum commitments, is able to produce post-quantum proofs. Okay, let's go further. Well, one thing. So what is part of this attestation? So attestation is this SNARK of a signature. So basically, it's a proof that certain signatures exist, plus as a public input, the bit mask. So bit mask of who exactly has signed. So the set of validators eligible to sign in this slot is public, but not all of them sign. Not every one of them signs, and those who sign, they get into bit mask. So basically, the proof certifies that if we select the set of validators according to this bit mask from the set of eligible validators, then there exists signatures from every one of them, and one signature for every one of them. that attest to this block. So for post-quantum possibilities, there are several combinations available. So we can deal with the lattice-based signatures. Some of them, like Falcon and Dilithium, produced by recent NIST project of post-quantum cryptography. There can be so-called hash-based signatures, and one of example is Sphinx, which is also there. And the second type is so-called signatures based on multivariate cryptography, or MQ signatures, but quite many schemes are broken in this area, and probably we shall not rely on them. So this is kind of too fragile a construction. Well, we have to design not only signature, but also mechanism to aggregation. So of course we can just collect them all, but looking into signature sizes, they're still too expensive to collect, to just plainly put 16K signatures on the blockchain. For lattices, there exist custom aggregation schemes or signatures that support aggregation out of the box. But well, this is not the subject of this talk. And third principle is if we employ PK proofs, constructions like SNARKs or GKR based on their post-quantum commitment. And this approach is somewhat better because it's modular. So if we separate proofs from signatures, then we'll be able to modify one of them if a problem occurs. If we, for example, employ custom aggregated signatures based on lattices, then we again put kind of all the eggs into one basket by relying on lattices on each step, like on the signature step and then the aggregation step. Whereas if we kind of use for proofs a different machinery than for signatures, then we can replace one of them without hurting the other, hopefully. Okay, so as you have guessed, and if you looked into the paper we have recently put online, we'll be talking of combination 2 and 3, basically hash-based signatures and post-quantum proofs. So why hash-based signatures are interesting for us before we go into concrete construction? So the advantage is, like, the construction is rather simple, at least for the variant of hash-based signatures that we consider. They reasonably small size, not the smallest one among post-quantum, but one of small ones. One important thing that the security of the signatures relies on very simple assumptions. We don't need any lattice assumptions. We even don't need collision resistance of underlying signatures. What we need is even a property that is weaker than collision resistance, so-called target collision resistance. And thanks to that, we don't have to assume that our function down there is a random oracle. Thanks to that, if we have random oracles in our proofs, then we don't actually put random oracles into circuits. This allows to have a more clean security proof for the entire construction. So the downside of this, of course, I have to warn about the downside that for efficient aggregation, we need not traditional hash functions, but some hash functions that are designed particularly for SNARKs, for post-quantum proof schemes, and they are all prime field based, so not a traditional hash function. So it is possible, kind of technically, to employ traditional hash functions like Ketchak, I mean SHA-3 or Blake, but our current benchmarks show that to aggregate them all, we just can't do it within the latency requirements for the single slot that we have now. So unfortunately, this moment it's not possible. So currently, it seems that we do have to rely on hashes that are smaller in circuits. So well, the quantum security of these hashes, and some of them is somewhat less studied. but this is actually true for many constructions. So there exists some research, but we expect more third-party cryptographic analysis, particularly in quantum scenario, to come. But there is quite some security margin there. So even if some quantum attacks appear, as long as they are not devastating, we expect that the scheme survives, of course. So, okay, let me start talking technically. So one very important construction block that we use is so-called one-time signature. So you may think one-time signature is needed. Well, the thing is we build our kind of multi-time signature scheme from one-time signatures. And it's important to understand how one-time signature works before we go further. So basically, the public key generation works as follows. So what you see here is a set of so-called hash chains. This means like we create a beginning of a chain, and then we iterate it a certain number of times. And so here we iterated it 4 times, and we create 5 elements of the chain. And each element encodes some part of the message. In this scenario, since we have 5 chains, then this encode numbers from 0 to 4. This also can encode numbers from 0 to 4, and so on. This means that kind of overall we can sign with this construction 5 to the 5 messages. And the public key of this construction is the hash of chain ends. So let me show you how actual signature works. It's fairly simple. So suppose we want to sign a message that belongs to the set of signable messages. Then it has 5 components, and each component is from 0 to 4. And suppose we want to sign the message 32303. And basically what happens is that we publish this chain elements. So we publish chain element number 3 from the first chain, chain element number 2 from the second chain, chain element number 3 from the third chain, and so on. We publish them all, and then in order to verify signature, it's sufficient to iterate the first element once to get into 4, to iterate the second element twice to get into the chain end, the third element once, the fourth element 4 times, and the fifth element just once. Then we obtain all the chain ends, we can hash them all, and then we check if the result equals to the public key. So why this construction is secure? Well, to make it secure, we actually require that we sign messages with only with fixed sum only. So in this particular construction, the sum of indices is 3 plus 2 plus 3 plus 3 is 11. And as long as we require that we sign on the messages with the sum of components equal to 11, you see it's not possible to forge a signature. I mean, it's not possible from a published signature to sign another message because, well, when you publish these chain components, it's possible to sign the message with each component which are further on the chain. But if we put this sum requirement, then another message with the sum 11 must have one of its components smaller than this one. For example, if we want to sign not 32303, but 23, if we want to swap these first 2 components to have the same sum of elements, then it means, well, we have to publish this element and this element, but this element remains secret in the custody of the private key owner. So just having the signature, I mean, this 5 components, it's important that it's not possible to produce another signature for a message with the same sum. The secret key here is our chain beginnings, but of course they can be generated from PRNG. This is very important concept, actually, this one-time signature. So if you have questions, I think it's time to ask. I can wait a few seconds if you type something. Okay, so suppose that it's all clear. So a little bit about the notation. So right now, I'm talking about hash chains of length capital W. Well, in our paper, you may be able to see that there is small w and there's 2 to the power of small w. So you see here, like in item 6, really this number, it's often the power of 2. It's actually to simplify a signature in order to sign a message which consists of bits. It's kind of, if we split the message into integer number of bits, then it's clear that we can. So, for example, if we split into pairs of bits, then each pair of bit corresponds to a chain with 4 elements inside. So that's why this big W, it's usually a power of 2. Okay, so what is the question that they ask? Why this scheme are quantum proof? Okay, so the security of the scheme is based on, I can see one wayness basically of hash function H, because sort of almost the only way to forge a signature is to find a pre-image to an already published signature. So in order to sign another message, you have to find a pre-image to at least one of them. And as long as hash function is quantum proof, then the entire construction is quantum proof. And for vast majority of hash functions that are deployed, they are quantum proof because they don't contain any quantum vulnerable machinery inside. Okay, so why actually one-time signatures are okay for us? Well, the thing is, we can out of one-time signatures, we can build multiple many-time signature, because we can pre-generate sufficiently many one-time public keys and put them all into a Merkle tree. And then whenever we want to sign, we just sign for the public key in the first leaf. Then we want to sign the second time, we use a public key from the second leaf, and so on. So in the particular beam chain scenario, if we, for example, want to sign 1,000,000 of times, means million slots, means like 10 days, several days, or a month or something, then basically we just pre-generate 1,000,000 signatures. And this is feasible because to generate 1,000,000 signatures, well, you need kind of quite some time, but this is parallelizable and doable overall. So to generate a single public key, it's much faster than the slot duration. The actual numbers you can see in our paper. So the second important thing is we can call our hash-based signature stateful, which means that when we talk about sign-in blocks, all slots are enumerated, and basically for every validator, we just know the actual slot they're gonna sign. So it's known for every public key that first time they sign from slot 1, the second time they sign from slot 2, and so on. So basically, we just go over slots and every time for every particular slot number, we just select particular public key leaf. So we kind of dictate to every validator which which leaf it should use. So it's less convenient for regular signatures we use on Ethereum to sign transactions, but in the context of the Beam chain, that's quite convenient because slots are kind of external ticks that tells us which signature where to sign now. So that's convenient, and because of that, we don't need a more sophisticated construction of hash-based signature like Sphinx, because in Sphinx, what happens, they want to use the same public key multiple times without, and every time to generate to do something different, and so that the verifier doesn't know basically how many times a single public key is used. So the sync construction is more sophisticated, and the resulting signature is also much bigger. But in our case, it's smaller and simpler. Okay, so some small parameters here. So I have described it as like we use in the single hash functions everywhere, but in fact, all hash function calls are different. That is necessary to have better performance, actually. It also a little bit pain in the ass for implementers, because what happens is that actually every arrow here uses a little bit different hash input. So not only it hashes kind of different message, different state here, but also the hash function is called with a different so-called tweak, which encodes the position in the chain. So like when we hash here, we know that we are in chain 1 in position 2 or something like this. And also all this hash function calls, they're different across users. So each hash function, it takes additional input like P and T, and you will see them in the paper, you will see them in the code. What's important here is that like P is unique to the user, whereas T is unique to the position in the entire tree. And every implementation must conform to this construction. So what else? So in our construction, we have tested two variants actually for hashes. So we tested SHA-3 for everything. This is not for aggregation, or at least not for like high performance aggregation, but it's still, I think it's a viable approach, and to see how expensive it might be to aggregate SHA-3 signatures. For faster aggregation, one would use Poseidon. So Poseidon, it's as a hash, it's slower when you just compute a hash, but it's faster to aggregate. So this means that to generate signatures, to verify actual signatures in the tree, it's more expensive with Poseidon, but to aggregate signatures, it's faster. So what constructions we have tested? We have tested lifetime of 2 to the 20 slots. So if each slot is like 12 seconds, this means like 10 millions of seconds, and which is about 100 days or something. So this is a viable parameter. This sort of means that after this 2 to the 20 slots are spent for every validator, then they have to regenerate their public key. And of course, the actual parameters, how frequently they have to regenerate the public key, they all depend on the final beam chain configuration. But what's important that we kind of support different lifetimes. The chain values that are there, the chain lengths, they are also powers of 2, but for smaller, and the exponents are also from a certain subsets, like 2, 4, or 8, which basically means that if we use 2, that means we split the message into pairs of bits, or in quadruples of bits, or 8-up, or into bytes. So this means that this parameter means we use like 70 something chains. Like you see here, we use like 78 chains, here we use 39 chains, and here we use 20 chains, but each chain is longer. So this actually is some sort of a trade-off. So why this trade-off? Means like smaller, fewer chains, but longer chains. And of course, the longer the chain is, the longer verification is. But on the other hand, the kind of fewer chains mean smaller signature. So there's a trade-off between verification and the size. Yeah, I will go into concrete numbers soon. So for key generation, how key generation happens in this construction, if we go into details. So basically, you're supposed to have like a single PRNG, a cryptographic one, of course. And with PRNG, you generate the beginnings of all chains in the entire tree. So if you use 2 to the 20 slots, then you generate like 2 to the 20 something chains, more than 2 to the 20, like 2 to the 20 leaves, and for each leaf, many more chains. Then you compute you compute chain ends, you compute the leaf, and from this leaf, you compute a single public key, and this will be the public key, actually. And you publish the root, so this will be user's public key. For signature generation, so how signature generation happens. So suppose we are now in slot 2 and we sign, we basically get a block value, which is M here. We hash it with a hash function like Poseidon or Shad or anything else, depending on your implementation, with additional parameters. We basically target certain checksum here. Actually, this checksum means like the total sum of positions, and it is taken to make kind of all this chain positions closer to the end, so that verification is faster. And this checksum t is heuristically taken to not to make the signature generation too expensive, but also to make verification faster. So basically, the first step in signature generation is to find a random counter that gives us the certain checksum. Then we produce this chain positions that sum to this checksum, and then we add this chain values into the signature. And after that, we also have to add the Merkle path here, so that verifier can go through the entire Merkle tree to produce the public key. So you see here, we add the Merkle path also. Of course, you may notice that if we kind of produce one signature after another, then it's possible to cache the Merkle path, and some elements you don't actually need because you can recover them from previous signatures. So like in this sense, there's some overlap, of course. Okay, yeah, now we can see some actual parameters. So what sort of happens for Poseidon, for example. So there is an extract from the table in the paper. The TSV stands for target sum winternits, and delta 1 means we target the average value, means like the all chain positions, they are kind of around the middle. And 1.1 means they are sort of by 10% closer to the end, which means that the number of hashing calls that are needed to be done, they become smaller. This is visible here. So what are the interesting numbers? So in this column, there is signature size, and signature size consists of, as we have seen, these entries and the Merkle path. So the Merkle path has the kind of same overhead of around 500 bytes, and the rest are these chain positions. So basically, the fewer chains, the smaller this part is. You can see, for example, if we use v = 1, means like we have only 2 elements in the chain. then our signature is almost 5 kilobytes, of which 500 bytes is the Merkle path, and 4 kilobytes are these chain entries, because there are like 256 chains, or even more than that. But since each chain is short, then to verify it, you only have to call 77 times Poseidon of width 16 and 93 times Poseidon of width 24. This is for public key hashing and for Merkle tree hashing. If we spend little more time, like you see that signature time is increased by 50%. If we target a sum which is 10% bigger, then we can have even faster, like even fewer Poseidon calls, like 69. But the signature size remains the same, just the signature generation time increases, the verification time decreases. There's another, following this trade-off. So if we select like a longer chain here, like chain with 4 elements, then the signature becomes almost 2 times as small, like it's 206 kilobytes, but of this 500 bytes are Merkle proof, and 2 kilobytes is the chain entries, but you spend more Poseidons here. You see, like, if you can have like 2 times a small signature, means like smaller bandwidth, but during aggregation, you have more Poseidons to compute. So in real network, we'll have to make a decision which parameter to select. But if you implement this over some real network, you have to choose either you use most of the bandwidth, and spend more time on receiving the signature and storing it, but then aggregation is faster, or you say, okay, I will devote less time to receive signatures because they're smaller, but then I will spend more time on aggregation. And this decision is, of course, well, for the beam chain, it was some global decision, but in particular implementation, you can play with it. And of course, everyone has its own arguments which one is better. You see, we can kind of aggressively push the signatures smaller and smaller, but the verification cost increases exponentially here. So at some point, it's not worth it anymore. Yeah. What else? Yeah. There are some concrete scenario which we think is interesting, is this one that I've underlined. So I give here, for simplicity, all the parameters, means like we have chains of length 4. In total, we have 78 chains, and we target the sum of indices to be 129. So like the positions are 0, 1, 2, 3 in each case, and we want all of them to sum to 129. The chain hash is the Poseidon over baby bear prime field, 31 bit. And we compress it to 7-word output, means like 28 bytes. So we don't even use 256-bit output hash function, because thanks to weaker security property, we don't need full collision resistance. So bigger Poseidon is used for public key and Merkle hashing, and you see like lifetime 2 to the 1.8 means lifetime of about 11 days if you assume 4-second slots. The total signature size, you see, it's like 78 number of chains plus 18 Merkle paths, each of 7 words, and this gives us 2.6 kilobytes. Yeah, what else? Well, there is the reference implementation, and I can spend some time to show you basically what is where. So the code on this prototype implementation is in Rust, and in the repo, which is public now, it's of course everything is an SRC folder. Let's see. Yeah. So you can see what's going on there. So basically, the entire thing is in the signature, and just by looking into tests, you can yeah, I think it's somewhere down there. Yes. So basically, there are some test instantiations of almost everything, like of hash functions, of the number of chains, on the lifetime, and so on. So all these signatures are generated and tested very quickly. This is with SHA. This is with Poseidon. So from test calls, you can figure out rather, I think, hopefully very quickly how everything works. And the actual parameters choice are in instantiations Poseidon and instantiations SHA. You see there are like several parameters. So we start with lifetime of 2 to the 18, and then there are certain numbers that we select, like the number of words in the hash length, the number of words when we hash the original block, the number of words for the tweak, the counter length, the capacity parameter for sponge hashing, and so on. Here are also the parameter, the number of chunks that we select. So they are all taken from the table, and you can use them as, so you using them, you implement exactly the parameters which I described in the table in the paper. So basically, if you go into Poseidon, then the parameters there, they exactly covering this set. They are all there, and kind of, I think you can figure out rather quickly which is which which is which. And I'll be available in our Discord room sufficient number of times to answer questions. And I think also it's good time to answer various questions from you guys on the presentation or on something else. Yeah, thank you for your attention.
Great. Well, thank you, Dimitri. I think we've got a couple of questions in the chat, but yes, as Eric says, if you post in the questions tab, that will be a lot easier.
Okay, what are the expectations for the hackathon project? Well, I believe that from my side, we would be super interested in seeing the entire implementation, not only of the hash-based construction, but also on the aggregation part. Actually, I see that I've missed one last slide where I described the aggregation circuit, but it's more like for a reference because I think it's pretty involved, and I will not go into that. But those who implement aggregation, they could use it as a guideline. So maybe other runners of the bootcamp could, would recommend some reading material to understand it better. Yes. So for hash-based signatures, I think the description in Dan Banet book, it's quite nice, and I think, well, maybe some slides about XMSS. So, for example, if I simply Google Dan Banet book, then kind of you see it's found in the signatures. I think message integrity from collision-resistant hashing somewhere there. You can find it just by googling the internet. You'll see it available. Also, there are some slides around. Actually, I probably should spend some time finding the literature, but I hope that the slides and paper are good enough also. Yes. Well, can I please recommend begin to intermediate notes or books that focus on foundational theoretical mathematical intuition in the subject. Yeah, well, I think this book is actually nice. For proof part, there is of course Justin Thaler book, which I think was referenced already. Yeah, I read it myself with yeah, I was quite excited when I read it. I don't think it covers this constructions because they're just PK signatures, but for the proof part, I think it's quite good explanation. Yeah, Git project. Well, this one that our prototype implementation is kind of complete. So to test it, to test the signature, you don't need anything else. For aggregation, of course, you'd need a different crates, but I'm not a good person to recommend any particular proof system implementation. I believe some other guys may help me to point out to particular kind of compile things created by you at Polyhedra and other things. I think that's the bootcamp runners can recommend it. So
Great. I think Kathy was asking if you could share the GitHub link with this Rust library in the chat potentially.
Yeah, well, they are in the slides. So if you have the slides around, then you should just click on it and it will be there. Yeah, if you want to make just a print screen or whatever.
Great. And also, as Eric said, there will be the other workshop later today in approximately 2 hours, which will be by Dan. So don't forget to miss don't miss that. Don't forget to tune in for that. Yes, Eric's put it in the chat helpfully. Yes, the slides are in the hacker pack. Let me send you the link in the chat here. Yes, any more questions for Dimitri? Those resources I'm sure will be very, very helpful. So yes, if anyone has any more questions, we've got a little bit more time. Just put them in the questions section. Oh, okay, I think we have another one.
Okay, have you considered UV signatures? Yeah, if I can remember correctly, UV is this multivariate cryptography thing. So, well, we have some sort of prejudice, I'm afraid, against multivariate cryptography. We kind of think that, well, it's interesting and performance is good, but well, I think we should wait a little more before relying on it. After all, this hash-based construction is like super old and mature. So for Ethereum, I wouldn't recommend using multivariate crypto at the moment, I'm afraid. Yes, so the ideas that I think the most worth to work it. So I think that what's really interesting is this trade-off between bandwidth and aggregation and amount of aggregation. So in the end, we'll have to make like a tough decision where to be if this signature type is selected for the bin chain. Then we would have like tough time selecting which parameter to take, and we do need like good arguments whether bandwidth or kind of amount of Poseidons is more important there. So whatever kind of provides arguments in one or in either direction is interesting, I think. And like all the network parts are interesting, all the aggregation parts are interesting. But kind of if you how you can aggregate, can you aggregate like in portions or something? Can you what kind of precomputation you can do if using lookups does lookup help? Do lookups help? And something like this. But I think this trade-off is the most important part to explore, and also the most difficult because it involves network reasoning. Yeah, very good question.
Cool. Any more questions? I mean, Dimitri, your workshop was really in depth, and you've been answering questions as we go along. So maybe we will have none. But if anyone does, please do pop them in the chat. Yeah, thank you, Dimitri, for this workshop. It was really interesting, really informative. As said, the recordings will be edited, uploaded on our YouTube and shared in the Polyhedra Discord channel, and also in the Hacker Pack. So you'll have the recording available in multiple different areas, as well as the slides that Dimitri has so kindly shared with us. So if that is everything, any final questions? Speak now. And yeah, if that's it, Dimitri, thank you so much. I hope to see you guys in a couple of hours at the second workshop today with Dan from Stanford. That'll be really interesting. And yeah, I hope you guys have a great rest of your day. Hopefully see you guys in a couple of hours. And yeah, thank you very much.
Yeah, thanks everyone. Thank you for listening. Yes, and thank you, Adriana and others, for inviting me. It's a pleasure to talk on our very recent research, and hope to see you quite soon.
Great, thank you very much. Have a great day, everyone. Bye.
Bye.